So here are features that you might consider when you're writing an advanced spam filter. For example, does the email come from a known spamming IP or computer? Have you emailed this person before? In which case it's less likely to be spam. Here's a powerful one. Have 1,000 other people recently received the same message? Is the email header consistent? So for example, if the from field says your bank, is the IP address really your bank? Surprisingly, is the email all caps? Strangely, many spammers believe if you write things in all caps, you pay more attention to it. Do the inline URLs point to those pages where they say they're pointing to? Are you addressed by your correct name? Now these are some features, I'm sure you can think of more. You can toss them easily into the naive Bayes model and get better classification. In fact, modern spam filters keep learning as people flag emails as spam. And of course, spammers keep learning as well and trying to fool modern spam filters. Who's going to win? Well, so far the spam filters are clearly winning. Most of them are spam I'll never see. But who knows what's going to happen in the future. It's a really fascinating machine learning problem. Naive Bayes can also be applied to the problem of handwritten digit recognition. This is a sample of handwritten digits taken from a US postal data set where handwritten zip codes on letters are being scanned and automatically classified. The machine learning problem here is taken a symbol just like this. What is the corresponding number? Here it's obviously 0. Here it's obviously 1. Here it's obviously 2, 1. For the one down here, it's a little bit harder to tell. Now, when you apply naive Bayes, the input vector could be the pixel values of each individual pixel. So we have a 16 by 16 input resolution. You would get 256 different values corresponding to the brightness of each pixel. Now obviously, given sufficiently many training examples, you might hope to recognize digits. But one of the deficiencies of this approach is it is not particularly shift invariant. So for example, a pattern like this will look fundamentally different from a pattern like this, even though the pattern on the right is obtained by shifting the pattern on the left by 1 to the right. There's many different solutions, but a common one could be to use smoothing in a different way from the way we discussed it before. Instead of just counting one pixel values count, we could mix it with counts of the neighboring pixel values. So if our pixels are slightly shifted, we get about the same statistics as the pixel itself. Such a method is called input smoothing. You can what's technically called convolve the input with the Gaussian variable, and you might get better results than if you do naive Bayes on the raw pixels. Now to tell you the truth, for digit recognition of this type, naive Bayes is not a good choice. The conditional independence assumption of each pixel given the class is too strong an assumption in this case. But it's fun to talk about image recognition in the context of naive Bayes regardless. So let me step back a step and talk a bit about overfitting prevention in machine learning, because it's such an important topic. We talked about Occam's razor, which in a generalized way suggests there is a trade-off between how well we can fit the data and how smooth our learning algorithm is. And in Laplacian smoothing, we already found one way to let Occam's razor play, which is by selecting the value k to make our statistical counts smoother. I alluded to a similar way in the image recognition domain, where we smooth the image so the neighboring pixels count similar. This all raises the question how to choose the smoothing parameter. So in particular, in Laplacian smoothing, how to choose the k. There is a method called cross-validation, which can help you find an answer. This method assumes there's plenty of training examples, but to tell you the truth, In spam filtering, there's more than you ever want. Take your training data and divide it into 3 buckets. Train, cross-validate, and test. Typical ratios would be 80% goes into train, 10% into cross-validate, and 10% into test. You use the train to find all your parameters. For example, the probabilities of a Bayes network. You use your cross-validation set to find the optimal K. And the way you do this is, you train for different values of K, you observe how well the trained model performs on the CV data, not touching the test data, and then you maximize over all Ks to get the best performance on the cross-validation set. You iterate this many times until you find the best K. When you're done with the best K, you train again, and then finally, only once do you touch the test data to verify the performance. And this is the performance you report. It's really important in cross-validation to split apart a cross-validation set that's different from the test set. If you were to use the test set to find the optimal K, then your test set becomes an effective part of your training routine, and you might overfit your test data, and you wouldn't even know. By keeping the test data separate from the beginning and train on the training data, use the cross-validation data to find how good the training data is doing under unknown parameters such as K, to fine-tune the K. And then finally, only once use the test data, you get a fair answer to the question, how well will your model perform on future data? So pretty much everybody in machine learning uses this model. You can redo the split between training and the cross-validation part. People often use the word 10-fold cross-validation, where they do 10 different foldings and run the model 10 times to find the optimal K or smoothing parameter. No matter which way you do it, find the optimal smoothing parameter and then use your test set exactly once to verify and report.